Hello, here we go with the next lesson on harder equations that are still going to be linear, but they may not appear to be linear at first. It may take a little work to get them to be linear. And in fact, that's the goal. Transform an equation into a linear equation and then solve it. We're actually going to start by sort of reminding ourselves how did the easier problems work in the previous lesson. This was about as hard as it would get in the previous lesson. First you would distribute, then you would combine like terms, then you would try to get down to a single copy of the variable on one side or the other, cancel addition or subtraction, cancel multiplication and division, and you'd be left with x equals number, in many cases within 5 steps or less. Okay, so now we're going to be looking at more of the idea of, okay, things we might have to do in addition to this or before this. Before we get started, we're going to actually look at equations that are a little harder because they maybe don't have a solution or they don't have an exact solution. And so there are a couple of vocabulary words I want you here to be aware of. An identity is an equation with infinitely many solutions, or it's always true. And so it would be equivalent to like 0 equals 0 or 1 equals 1, something that's just always true. An inconsistent equation, on the other hand, has no solution and it's always false. So it would be equivalent to 0 equals 1, since that's never true. Well, you don't hear me say this word a lot, but it's out there, so I want you to be aware of it. Conditional equations are what you're used to working on. There's a definite solution set, and it's true for some values, but false for others. And so it's like equivalent to x equals some number, and that number is one of the solutions. So let's pause there and make sure we understand this. I've got two equations here in the example, so we're going to solve these and see if we can figure out which is which. So maybe we start with a little distributing. 3 times x is 3x. 3 times 1 is 3. Nothing else in the problem changes yet. Some of you probably already see where this is going. What's 3 plus 3 makes 6. And now we need to get our variables together. So we subtract 3x on both sides, and look at that. We're left with the statement that 6 is equal to 7. Well, I'm pretty sure that's always false. Or in other words, there's no solution. Directions actually say to write either no solution or infinitely many solutions for this problem. Or if we wanted to throw out our fancy vocabulary, inconsistent. I might use this word some. We'll probably use no solution the most. But I want you to hear about inconsistent equations somewhere else and wonder what they were. Well, Mr. Carpenter hasn't taught me that or whatever. And no, I have. We just don't use that word as much. You could think about what it means in real life to be inconsistent, like it doesn't make sense. Alright, so this one we distribute 3 times x plus 4, we get 3x plus 4 minus x. It's a little messy, let's see if I can. 3x plus 4 minus x is equal to 8 plus 2x plus 4. Combining like terms on both sides, well, 3x minus x is 2x. 2x plus 4 equals, well, I made a boo-boo right there. That's not good. 3 times 4 is 12. Mr. Carpenter, not distributing correctly. I can't believe you would do that. Oh well, it happens. 8 plus 4 is also 12. So 2x plus 12 equals 2x plus 12. A lot of you probably already seen what's going to happen here. You subtract 2x on both sides, trying to get your variables together. You get 12 equals 12, which is always true. Which means there are infinitely many solutions. Please, oh please, oh please, don't abbreviate this. I know it's a lot of writing. I see a lot of students that want to abbreviate this to IMS. That doesn't mean anything to anyone other than you. Granted, I can figure it out, but you're not supposed to make up your own abbreviations until you're famous and other people are actually willing to pay attention to what you have to say about it. So if this one's inconsistent, this one would be consistent. But we're going to use the word identity here. Okay? It is consistent dependent, but I'm not going to worry about that. Making you all use that correctly. So just say it once. It's consistent because it has a solution. It's dependent because there's more than one. Alright, so that's good. We figured out which is which. Okay, back to presentation. Not much else. Let's see, there's nothing else there. That's right. All that's left are examples. So here are two problems we're going to solve. They don't look like a standard linear equation. They don't look like number times x plus or minus number equals number. They don't look like this. But we can make them look like this. This is a proportion, so we can cross multiply. So 4 times 3x minus 5 equals 5 times x plus 3. After you cross multiply, you actually get a less complicated version of this problem. This is like a problem that maybe has already been cross multiplied. We distribute the 4. 12x minus 20 equals, well, we distribute the 5 as well. $5x plus 15. Excuse me. We subtract 5x on both sides. Well, 12x minus 5x is 7x. Equals 5x plus 15. Excuse me. I got distracted by erasing that, and I forgot that I'd already subtracted the 5x. Excuse the technical difficulties here. There we go. Let's white all this out. Try again. You subtracted 5x on both sides, so over here is just 15. Add 20 to the other side, 7x. It's 35. Divided by 7x is 5. Trying to describe what I'm doing at each step. I'm not actually writing like the word add or subtract, multiply, dividing, or like we did in the last lesson, so just be aware of that. Be real careful on this one. Let's go switch to purple for a second. Okay, so we need to distribute here very carefully. A lot of you will call this FOIL. X times x is x squared. X times 2 is plus 2x. Negative 3 times x, negative 3 times 2. So minus 3x minus 6. Right, I'm going to run out of space here if I'm not careful. Same deal, let's distribute on the other side. X times x is x squared. X times 1 is plus x or plus 1x. 4 times x and 4 times 1, so plus 4x plus 1. Combining like terms on each side, we would have x squared minus x minus 6 equals, we just combine our like terms right there, equals, yeah, we got some combine on here as well, x squared plus 5x plus 1. We want to get our x squareds together, so we'll subtract x squared on both sides. A lot of you have probably already figured out these x squareds end up canceling each other out. Let's add x on both sides, because I want to avoid the negative. So add x, we get 6x plus 1. Subtract 1 on both sides. Divide by 6, we would get negative 7/6. It's equal to x. Symmetric property will let us turn that around. Now, it's not too hard to check the 5. 5 plus 3 is 8. 4 over 8 reduces to a half. 3 times 5 is 15. 15 minus 5 is 10. 5 over 10 also reduces to 1/2. So this one's definitely right. This one would not be nearly as enjoyable to try to check by hand, but you could substitute this number in for both of these x's. It's going to do this maybe on a calculator, get it multiplied together. Then do the same thing on this side, get it multiplied together. And you'll see that you would get the same number on both sides, and that would be your check. I'll leave it to you to do the check, because it would just be time consuming, and I don't want to waste your time watching me do a check. Hopefully I did it right. Let me just real quick convince myself, that I did it right. Let's see. 2x, 3x minus 6, negative x, negative 6, squared, 6 plus 5x. You know what? I knew that something felt a little off. 4 times 1. That's 2 mistakes in one presentation. I am not with it. That should be a plus 4. That should be a 4. That should be a 4. That should be a 4. Had you caught that yet? Now, if you had caught it, would you have asked me in class about it? Hopefully the answer is yes. I suppose I could have gone with a teacher standard, pretend I was just testing you. But no, I really did just make a mistake. It happens. There, got rid of most of the evidence. I could be real clever and go back and recut this, re-edit it, but no. I'd rather you see me make the mistake. Still have one little mistake actually. Apologize for wasting your time. Let me fix this. Big thing was, though, I managed to catch it before I made it too far away. It just wasn't feeling right. I felt like I had done something wrong. I had to go find it. Alright, subtract 4 should have been negative 10, not negative 7. So divide by 6. Doesn't go in evenly, but that fraction reduces. See, I thought I'd remembered this one having a fraction that reduced. That's why I stopped and thought about whether or not I was right. Cut both of those numbers in half. -5/3. Still not beautiful, but it is hopefully correct now. Alright, so now we've got a problem with a 5/3 that we're going to distribute. And so we would have 5/3 of x. And if you need to, you pretend that 2's over 1. So -10/3 plus 4 equals -23. And then at this point, I would actually subtract 4 on both sides without trying to get these combined. So again, this lesson is kind of more about breaking some of the rules or having to add on to the rules. So we have two parts that involve a fraction that's thirds. We subtract 4 on both sides to get down to just a single number over here. And then, out of nowhere, thin air, we choose to multiply by 3. I call this fraction busters. Both of these are examples of fraction busters. And I always, when I teach this lesson in person, I usually make a really bad pun here about how teaching you fraction busters because we ain't afraid of no fractions, which is a Ghostbusters reference, which is now a really old movie that probably less than half of you have seen, so it's terrible. Anyway, when you distribute this 3, we picked 3 for a reason. You distribute this 3, it's going to cancel both of these 3's. You'll just be left with 5x minus 10. And then you need to multiply the -27 by 3 as well. Well, 3 times 20 is 60, and 3 times 7 is 21. So 60 and 21 makes 81. Add 10 on both sides. To get -71 divided by 5. -71 fifths. Which, if you insisted on trying to convert that to like a decimal, let's see, 5 goes into 70, 5 into 50, 10, 70 is 20 more than 50, so 4, so like 24.5, I believe, -24.5. It's the number that will make this a true statement. This one's a little tougher because you get fractions off. It's a two-step equation, so to speak, but it's got that format of ax plus b equals number equals c, or you could easily turn this into like ax plus b equals 0. The problem is all these fractions. I know you all hate fractions. So to start this problem, you actually need to think about what would be the least common denominator or least common multiple for all the numbers involved. 4, 5, and 10. And you can cheat a little bit because 5 goes into 10. So you don't even have to worry about the 5. You can say, well, what's the least common multiple of 4 and 10? And hopefully you'll come up with 20. And so we're going to multiply the entire problem by 20. So we'll multiply by 20 on the left. And the right. And when we distribute the 20, remember, we picked 20 because it's going to make the fractions go away. So 5 goes into 20 4 times. 4 times 1 is 4, so 4q. 4 goes into 25, so when we distribute 20, we would get 4 into 20 is 5. 5 times 3 is 15, so minus 15 equals, well, 10 goes into 20 twice, and 2 times 7 is 14. So here's an equation that's equivalent to this original one, but of course it's much, much easier to look at. You add 15, get that 4q. 4q is 29. So q is 29 fourths. And again, I hope I'm doing these right, even though I messed that one up earlier. I'll leave it to you and your calculator to sort of do the checks. We're already looking at about 20 minutes into this. And all we've done is a few examples, but these take a little longer because there's a lot more work. So these two are kind of like fraction busters, except the denominators are variables, which should totally freak you out even more than a normal fraction would. And so the idea is, okay, what would the common denominator be in these cases? Well, here the denominators are x, 1, and 3x. And so we need something that x and 3x both go into, because the 1 doesn't really matter. X goes into 3x, so we can actually cheat. And we're going to choose to multiply both sides by 3x. Let's actually start on the right hand side. The 3x's would cancel, and we would be left with 2. A little more interesting, we distribute right here. We have to be very careful. The x will cancel the x, but the 3 is still there, so 3 times 4 is 12. 3x times 7 is 21x. And so here's something that is equivalent to this original equation, except for one little teeny tiny flaw. In the original problem, because the denominator included an x, we know we can't divide by 0. So we got to keep in mind while we're working this problem, if we happen to get 0 as the answer, x can't equal 0. So the original problem would have no solution. And that may or may not happen on problems like this when you do them. Let's see. Subtract 12 on both sides. 21x is negative 10. And then you can divide by 21. And negative 10 over 21 seems to be the answer. When we check that, it should work. Again, checking that on a calculator be a little tedious. You should be able to see that you get one number for this side and the same number for this side. Okay, this one, I think I honestly need more room than what I've given myself. Let's try that again. Let's cut that off. This one. And I'll create a new page. And cheat and move this up here. And now I got the whole page. Alright. Okay, well, first and foremost, let's talk about the denominators. We got situations here. Kind of like lesson 5. What could x not equal? Well, x cannot equal x cannot equal 3, because that would make this denominator 0. X cannot equal negative 3. And with a little thought, you can probably convince yourself that 3 and negative 3 would, either one would make this denominator 0. And so these are the two values that, if we happen to get either of these as solutions, they won't actually work. I'll also give you a little hint on this problem. if you take the two denominators on the left hand side and you distribute those together, just like scratch work before we even start the problem. Distribute these together, you get x squared plus 3x minus 3x minus 9. Well, these cancel and you're left with just x squared minus 9. Which you might notice, that is the denominator on the right hand side. And so one of the tricks to this problem is that when you multiply these two denominators together, you get that. So what happens is that you're going to actually choose to multiply both sides by both of these denominators. Okay? You're going to choose to multiply both of these sides by both denominators. And, lots of things are going to cancel. So this one's kind of a tougher one compared to what we have been doing. So first, I just kind of want to look at what would happen on the left-hand side. Well, we have these two things, and we're going to distribute it, but what we're distributing to are fractions. And so when we distribute here, the x minus 3's cancel. And we would just have x plus 3 times 1, which is x plus 3. Likewise, when we distribute these two pieces, both of them, well, the x plus 3's cancel now, and so you'd have x minus 3 times 1, which is just x minus 3. And when you multiply the right-hand side, 1 over x squared minus 9 by both of these pieces, since you got to multiply on both sides to keep it balanced, the denominator would cancel completely out and you're left with 1. And so it might be a little hard to believe, but this original problem, with a little bit of trickery, is equivalent to this much simpler problem. Well, x plus x is 2x, and the plus 3 and minus 3 cancel out, and you divide by 2, and it turns out the answer is 1/2. And you might be saying, I'm not sure about that one. So I thought we might work one or two like this in class. So we'll do one here together, and I figure we'll probably do another one or two in class. It's pretty tough. I doubt you've seen anything quite that complicated. I really honestly am more interested in, for right now, can you do this type? But I thought I would throw in one that was kind of easy of this type, just so you could see where we're going with it. So that'll be it for right now. Good luck with these, and I'll see you in class. See you next time.